Hey everybody, here's the solution for case 3 of the mass striking the rod for conservation of angular momentum examples. I erased the entire board and then I figured that you need to see the solution anyway, so I just spent the last 5 minutes rewriting what was already on the board. Let's work out case 3. You can check your answers and make sure that the answers you got match my own. Okay, so for case 3, conservation of angular momentum still holds. Initial angular momentum of the entire system is equal to the final angular momentum of the system. Again, initially, it's always the same initial setup. We have mvr, which is just the angular momentum of the ball, right as it hits the rod. That's equal to the final angular momentum of the system. Here you have to be very careful how you set up your positives and your negatives for the two objects in this system. Now we have two objects separately moving after the collision. We have the rod rotating clockwise, and then we have the ball moving downwards, which according to this axis here, this is in the clockwise direction. So this momentum is going to be negative, and this one's going to be positive. Okay, so let's start with the rod. We have I for the rod multiplied by omega. Now, when this object bounces off, it's not moving rotationally about this axis. It has the linear momentum some distance away from the axis. So it actually has the same expression as before with our new velocity bouncing off. We said that speed bouncing off is going to be 2 meters per second. It's going to be in the opposite direction. This is clockwise, so we're going to subtract off m. This is v initial. This is v final. And that's multiplied by r still. Again, when we look at these collisions, we're looking just before it hits the rod and just after it hits the rod. So we can assume that everything is happening right at that spot. Okay, now based on this setup, how is this going to affect our omega? Let's work it through, and we'll plug in what we know, get an expression, and then we'll calculate it out based on the given information. Okay. So we're going to plug in what we know about the rotational inertia of the rod. That's 1/3 mr squared. We're going to move over this term and start solving. So we could say that mv initial multiplied by r plus mv final multiplied by r is equal to 1/3 capital M for the rod, r squared. That's the rotational inertia of the rod. And that's it. So we're going to pull out these common terms, which is mr, divide over mr squared multiplied by omega. There we go. Pull out the common terms, divide over, so we have omega alone. We'll compare the expressions. Again, simplify the expressions so you can clearly compare for case 1 and case 2, and then we can plug in our numbers and solve. So we have mr is common in both these terms, multiplied by vi plus vf. Now, make sure you plug in the speeds here. We already took direction into account with our setup. So now that we took direction into account here, we're just plugging in +8 and +2. Just plugging in our magnitudes. This is going to be divided by 1/3 mr squared. That 1/3 makes it so there's a 3 in the numerator. That's capital M r squared. Once again, one of those r's go away. And we're going to get 3m, little m, multiplied by the sum of the initial speed, the final speed, all over capital M R. This is lowercase, this is capital. Make sure it's nice and pointy for you. That's going to be equal to our omega. Now, again, compare this expression to the other two before you plug in numbers and solve. As you can see, our numerator increased because for case 1, we were just multiplying by that initial speed. Here we're multiplying by the sum of the two, and the denominator stayed the same. This omega, based on our other two cases should be the greatest omega out of all three, which makes sense because if angular momentum has to be conserved, if this one's bouncing back, this has to spin at a greater rate to make sure that angular momentum is completely conserved. It has to compensate for this now negative angular momentum after the collision. Boom. All right. Plug in your numbers, work it out, check my work because I can make mistakes. But when I worked this out, I got an angular velocity of 3.75 radians per second. Just like we thought, the greatest out of all three. Now, something else I want to discuss too. When we were looking at linear momentum, we were analyzing elastic collisions, inelastic collisions, and seeing if kinetic energy is conserved between the collisions or not. It's a little more complicated with angular momentum, but we can look to see if kinetic energy is conserved throughout all these collisions. And for some of them, you're actually going to find that we gain kinetic energy from initial setup to the final setup. How could we possibly gain kinetic energy? We have to remember that the fact that we fixed this axis so it can't move means that we're adding an external force to the system. Not an external torque, but an external force. You can calculate the difference between the kinetic energies. Keep in mind that if something's moving linearly, energy is a scalar quantity. We don't care about any kind of frames of reference or anything. This would have translational kinetic energy, which is 1/2 mv squared. And then when something's rotating, it has angular kinetic energy, which is 1/2 I omega squared. If you'd like, go back through the cases and calculate the kinetic energies for each. If you're surprised, again, just keep in mind that we have this fixed axis, allowing the rod to, forcing the rod to rotate about one of these axes. All right, and that's it. That's the solution for case 3. Again, let me know of any kind of videos you need, and I'll see you soon.